let's get hands-on and start playing a little bit, right? So let's observe something. So 4 power 50, right? So this is, so 4 power 50, you can actually write like this, right? Using your basic high school math. So 4 can be written as 2 power 2. So 4 power 2 can be written as 2 power 2 to the power 50, which is nothing but by using the power law. So a to the power m to the power n is a to the power mn. You can multiply these two things, right? It's a basic thing, right? So 4 to the power 50, you express it as 2 power 2 power 50, express the 4 like this, then you get 2 power 100. So what is this actually telling us? So actually, if you find 2 power 100, you don't have to find 4 power 50, because the value of 2 power 100 is nothing but the same value for 4 power 50, and in the terms of this problem 4 to the power 50 is a non-distinct power because its value is already computed while computing 2 to the power 100. And let's play a little bit more with some more real examples. So consider 16 to the power 20, right? 16 can be written as 2 to the power 4, right? So 2 to the power 4 power 20, so which is nothing but 2 to the power 80. And 16 can be written as 4 to the power 2 also, right? So 4 to the power 2 power 20 is 4 to the power 40. So what we are seeing here is, while you compute 2 to the power 80, so if you compute 2 to the power 80, you are in turn finding the values of 4 to the power 40 and 16 to the power 20, right? So you could find something more, but in this case example, I'm just saying, like, if you find 2 to the power 80, you are finding 4 to the power 40 and 16 to the power 20. And in terms of the problem, 4 to the power 40 and 16 to the power 20 are non-distinct powers. You shouldn't count them because the same value is obtained while computing 2 to the power 80. Now, I think there is a pattern that you could generate if you start observing that you could express it as a power, and you can see that, right? So basically now you have to ask a question, or what, like, you have to generalize the pattern a little bit. So you look at it in two ways, right? So what's a top-down way, right? So the top-down way is while computing a bigger power combination, right? So let's say while computing 16 to the power 20, what are the smaller power combinations that yield the same result? So that is top-down way. What is the bottom-up way? So while computing a smaller power combination, let's say while computing 2 to the power 80, what are the bigger power combinations that yields the same results? So while computing 2 to the power 80, what are the bigger power combinations that yields the same results? 4 power 40, 16 power 20, etc. So you could look at this in two angles, and now I think it should strike you a little bit, right? The key insight should strike us now. Do we really need to compute the actual power combination values? Probably no, right? We don't have to. So we'll take this thought apart, right? So what is the key idea here? If you remember the table, why I told visualizing this as a table is helpful. So now this is the same table that you saw in the first slide. 2 to 100 in the row wise and 2 to 100 in the column wise. But if you see, I am putting 1 and minus 1 in each of the cell value instead of actually computing the cell value, right? So instead of computing actually 2 to the power 2, I am putting a 1 here. So what does this mean, right? So I can encode this table in such a way that I will put the cell's value as 1 if the power combination of that cell is not computed before. So if 2 power 2 is the first time it is going to be computed, it's not computed before, means I will put it as a 1. And let's say 2 to the power 4 is 16 and 4 to the power 2 is 16. So if I find out that 2 power 4 in turn yields the smaller power combination 2 power 4 yields the same value for the bigger power combination 4 to the power 2. So I will put a 1 for 2 to the power 4 because it has to be computed, but I will put a minus 1 for 4 to the power 2. So what is the idea? When I finish traveling this entire grid, putting 1 and minus 1 for every cell. So put 1 for a cell where you have not computed that value before, and put minus 1 where a smaller cell's computation would yield actually that value. Then the ask is very simple. You just have to count all the ones in this grid, and then that's it. You are done. The problem is solved. We have found the total distinct powers. So this is the key idea that we will use to solve this problem.